Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video, we're going to go ahead and continue our delving into the fundamental theorem of algebra by attaching to that fundamental theorem of algebra the complete factorization theorem and a few other sister theorems. Actually, I think in this video, I might just stick with only the complete factorization theorem just to keep it clean. Now, just to remind you, the fundamental theorem of algebra states the following. Every polynomial with complex coefficients has at least one complex zero. We're going to need that piece of information for our proof of the complete factorization theorem. Speaking of which, the complete factorization theorem states the following. If you have an nth degree polynomial, then it can be factored into the product of linear factors of the form a times, that a is just a leading coefficient, so that can be factored out. But basically into x minus c1 times x minus c2 all the way down to x minus c sub n. Notice I stated this is an nth degree polynomial, and you have 1, 2, 3, 4, 5, 6, and so on and so forth, all the way up to n linear factors. That's critical. C sub I here are all complex numbers, by the way, so they might be 5s, they could be I, they could be 3 plus I, they could be pi. All of those are complex numbers. And I went ahead and wrote down that there are n of those linear factors. This ends up being, I think, more important or more useful than the fundamental theorem of algebra, because the fundamental theorem of algebra just tells us, hey, our polynomial has a complex zero. But this one tells us not only do you have a complex zero, you actually have n of them. So this is a complete factorization. So this kind of extends the fundamental theorem of algebra to say, yeah. If you have a 10th degree polynomial, the fundamental theorem of algebra states, well, then you have at least one complex zero. This one says, no, you have actually 10 of them if it's a 10th degree polynomial. That's really cool. So let's go ahead and prove this. I'm going to zoom in here. Remember, we want to prove that polynomial has that factored form there. Well, one thing I know let's go ahead and be very, very careful with how we start this proof. This is not an if-then looking theorem, right? As I've been kind of focusing on, most theorems are of the form if P, then Q, right? If some statement is true, then some other statement becomes true. And you follow the proof by assuming that the first statement is true, and then you use logical deductive methods and arguments, definitions and theorems to showcase the antecedent or the result must be true. In this theorem, it just says, hey, every nth degree polynomial can be just factored into these n linear factors. Yay, that's all it says. There is no if then that we can see, but actually there is an if here. If you rewrite it, if you want to rewrite it, you could rewrite it as follows. The if part is if P is an nth degree polynomial. That's all we need. Technically, I will say this, we actually need it to be an nth degree polynomial with complex coefficients. Well, that's pretty much any polynomial. Then it can be factored into the product of n linear factors. So I'm going to go ahead and start my proof by assuming we have an nth degree polynomial called P. There we go. So let P be an nth degree polynomial. Now, one thing we know from a recent theorem called the fundamental theorem of algebra is that if you have an nth degree polynomial, then you know you have at least one complex valued zero. Let's go ahead and call that zero C sub 1. So call this C sub 1. Well, that will imply, now what I'm about to write is by the factor theorem, and I'll write that off to the right hand side, that will imply that P of x can be factored into x minus c sub 1, because c sub 1 is a 0, times some remaining polynomial, which is 1 degree less. So I'm going to call it p sub n minus 1 of x, because this was an nth degree polynomial. And now we have divided out 1 power of x, so now it's an n minus first degree polynomial. And finally, I just write off to the right-hand side there that this is true by the factor theorem. Well, now notice p sub n minus 1, that is also a polynomial, right? It's a polynomial of n minus first degree, and we know, again, by the fundamental theorem of algebra, that p sub n minus 1 must have a complex 0. Let's go ahead and call this complex 0 c sub 2. And again, by the factor theorem, this will imply that p sub n, we'll just stick with that one, is equal to x minus c sub 1. Oops, got a little overexcited about that c there. Times, now we know that c sub 2 is a 0 of p sub n minus 1, so x minus c sub 2 will factor out of p sub n minus 1, reducing the power of that polynomial by another one. So now we have a new polynomial, p sub n minus 2. You can repeat this process over and over and over again. As long as you have enough power, you could factor out another linear factor. And so performing this process repeatedly, we get that p sub n of x is equal to. Now, I do want to say here, there is something about the linear factors that might not work exactly like the original theorem. And we arrive at this, and I do want to do a little explaining here. So we've done this repeatedly, but I reserved the final statement for here. So we've split apart or factored out, or said that each step of the way we have a 0. So the first polynomial had a 0 at c sub 1, and then the second polynomial, this guy right here, has a 0 at c sub 2, and the next polynomial has a 0 at c sub 3, and so on and so forth down the line. Now we're about to finish, and we have one remaining polynomial left. That remaining polynomial is a degree 1 polynomial. Now the thing I need to tell you here is that degree 1 polynomial is not guaranteed to be x minus c sub n. It's not guaranteed to be that, because it might have a lead coefficient on that x. So we need to actually say that this is a times x minus some number. And this is, I'm going to erase this in a moment, but that polynomial, a linear polynomial, might be just 3x minus 4 or something like that, right? So I need to be able to factor that a off of that. And if I do that, I get this, and that c over a, I'm going to call that c sub n. So it's a little bit of a hand waving. It's not really, but it's a little bit of a hand waving in the end, because I'm not really going into detail about that. But the idea is the final polynomial likely looks like this, the final linear factor, and we're just going to factor out a off that. And so when we do that, we get the following result for our nth degree polynomial. It's x minus the first 0 times x minus the second 0 all the way down the line to x minus the n minus second 0, x minus the n minus first 0, and x minus the nth 0. And then we factored out of all that, which I forgot to do, an a all the way out front. There you go. So that is the proof of the theorem. QED. A really nice theorem, kind of a toughie to prove, but that is the full proof of the complete factorization theorem. The main thing that you need to remember is you're going to be using this. You're going to be using this to help you graph. So somebody hands you a polynomial, now you can dissect that polynomial into its component pieces, or at least you have a theorem that says you can. Now, just as a heads up, there is actually a theorem that logically flows after this theorem, after the complete factorization theorem, but it's probably a good idea just to showcase the complete factorization theorem before we continue. Now, if I was teaching this in a class, I would say, okay, everybody, I need one rational number, one integer, and a 3-term prime quadratic. And I do that for several reasons. So I'm going to just throw some numbers out, I think that you, as you're watching this video, should just go ahead and create, write down one rational number and one integer right now. I'll pause the video. And then go ahead and create a 3-termed prime quadratic. Now remember, I'll just go ahead and write down what I think what I want my zeros to be. So I'm going to say C is equal to 3/7 maybe. And so that's my rational number. And my C sub 2, which is my my integer, I'm going to have as negative 2. I don't want these to be absolutely huge though. So, and then finally, I need a 3-termed quadratic. So x squared, x, and a constant, but I want it to be prime. And this is a good time just to remind you that if you want a prime quadratic, something that's non-factorable over the complex or real number, well, over the real number system, you want your discriminant, focus in on this, you want the discriminant of that, which is b squared minus 4ac, you want that to be less than 0. So just think of some numbers right now that you would plug into b, a, and c that would force that expression to be negative. Obviously, you would like b to be not super large, don't go crazy, but something generally large. So I'm going to choose b to equal 5. You don't even have to have it positive, but I'm just going to do that. And maybe I'll choose a to be 1 and c to be 3. Maybe I'll do that. Let's see, b squared is 25. Minus 4 times 3. Nope, that's not good enough. So maybe I'll choose a to be, maybe I'll just reduce b down a little bit. Let's let b be 3. If you do that, b squared is 9. Minus 4 times 1 times 3 is minus 12. That's a negative number. We're good. All right, so it just took me a couple of moments to throw something together. So now I have a 3-term prime quadratic as well. So I'm going to write that down. 1x squared plus 3x plus 3. That's A, B, and C. Now I'm going to pause the video again. I want you to create a prime quadratic with 3 terms as well, because you're going to do something with me on the side. So I'm pausing. Now something we need to do prior to jumping into this is to massage these numbers a little bit. So if I told you that x, which is 3/7, is a root, and x, which is -2, is a root, you have different roots on yours. Go ahead and move everything to the left-hand side, and specifically get rid of fractions. So for example, in this first one, I'll multiply both sides by 7, and then I'll subtract 3. And on the other one here, I'll just add 2 to both sides. Right. So those will be factors for the polynomial. Now, I just want you to know that when we do what we're about to do, it's because I'm teaching you how to build your own examples. I'm also teaching you to do what your instructor or your professor probably does when they build examples for you to do on exams. They just kind of create answers and then build the questions. And here's our secret voodoo right here. So I'm going to take those factors, take your factors that you just created. Mine was 7x minus 3 and an x plus 2. And we also had the x squared plus 3x plus 3. Now, you could add powers on those if you want to. I'm not going to, but you could totally add powers on those if you want. And I just hit enter. Now I'm in Wolfram Alpha, by the way. And it's just computing this out to where it tells me what the expansion is. And you can see it right here. This is the total expansion of it. Normally I wouldn't do it for such a small polynomial expansion, but I'm just letting you know that if you wanted to create your own example, you could put a square on that and a cube on that. I think I've mentioned it in a previous video though. When you have large numbers at the constant position and you have large powers, things get out of control. So it's a little bit safer to not do that. Anyhow, I'm going to go ahead and copy this down. And here we are. And what we're going to do is use methods from this course. I'm going to highlight the actual question to completely factor this polynomial and state the zeros of this polynomial. So we already know the zeros and we already know how it factors, but let's pretend we don't. This is how you practice for exams and stuff like that. If somebody handed you this polynomial and you didn't create it, then you have a little rational roots theorem to go through, right? So remember the rational roots theorem, you talk about the constant versus the leading coefficient. Our constant being negative 18, but I just write down 18. And then the leading coefficient being 7. There's no reason to have the plus or minus the sign of the constant or the sign of the leading coefficient right now. What you're really worried about is just what is the magnitude of that number so you can figure out the factors. And the factors of 18 are plus and minus 1, plus or minus 2, plus or minus 3. Those are all the numbers that go into it. Plus or minus 6, plus or minus 9, and then plus or minus 18. 7 is easy, right? Plus or minus 1 and plus or minus 7. Those are my only options. And remember, my advice when using rational roots theorem is to kind of stick easy first. So let me write down the candidates. These are the candidate zeros. Maybe I should even write that in. And like I said, I'm just going to start with plus or minus 1, then move to plus or minus 2. I might do a plus or minus 3, maybe. But if none of those work, I don't want to go to the 6. I'll probably start with a plus or minus 1/7. And oops, that was supposed to be 1/7, and a plus or minus 2/7. And if none of those work, then I have other work I have to do. So let's go ahead and try. So again, I happen to know the background story here of how this will factor, but let's pretend that we don't. Let's just pretend it's an actual homework. So testing the 1 to see if 1 is a 0, bring down the 7, and you know the rest, right? 1 times 7 is 7, add up. And I'm just going to go ahead and pause the video and finish out this line. And I don't even need to finish because I can easily see this is not going to work here. So I just move on to the next one, right? So I'll now do the -1. And just to showcase my thought process here, when I get to this point where I have 48 minus 25, I feel very good about this. But again, you just never know. But I now have a -23 here. 15 minus 23 is -8. And -1 times -8 unfortunately doesn't do it, right? This is non-zero right here. So again, -1, that's also not a candidate 0. Or it's not a 0. It is a candidate, but it's not a 0. Let's try 2. And I only have to go about that far before I realize this is just not going to work out. Because every time I get a result, it'll be positive. I'm going to double it, add it to another positive, double that result, add it to another positive. It's just going to grow. It's going to get huge by the time it gets there. So I know that 2 is not a 0. You can try it out if you want, but I'm telling you, 32 plus 14, what is that, 46? Double that up. You're already in a 92, right? And then you add those two together. It just gets larger and larger. So I'm just going to not follow through on that one, and I'm going to switch to -2. And here we go. We have our first winner. So it took a while to get there, right? But I'm using little tricks to help speed up the process. I'm using the fact that numbers, if they continue to grow huge and huge and huge, there's no point to continue that. In fact, I could have stopped that with this one as well. But now I know x minus a -2 is a factor and x equals -2 is a 0. So my polynomial, I'll just write up here, is equal to, oops, well, I'll just leave it that way, x minus a -2, which is x plus 2. And then we're left with a polynomial 7x, let's see, what was power x to the 4th? So 7x cubed plus 18x squared plus 12x plus 18x squared plus 12x, and finally -9. Now here's the deal. If that was, if you saw a pattern there, I would immediately do factoring by grouping, but I don't see a pattern there. So I would continue my process here. I'm going to try -2 again, even though you and I both know that -2 does not actually is not another 0, but let's just go ahead and do it. And there you go. I've just shown that -2 is not a 0 twice. So now we're done with plus or minus 2, and we'll go to plus or minus 3. And like I said, I will probably quit after plus or minus 3 and move on to my 1/7 and my 2/7. By the way, taking a note from our previous work, if I start writing down 3, how many times does 3 go into, 7, 18, 12, and a negative 9. That's the polynomial we're dividing into now. You bring down that 7 and multiply it by 3, it becomes 21. You add those two up, you know it's going to be a larger positive number. This is a large positive number right here. What is that, 90, 127 or something like that, 117? So it just gets larger and larger. I know that that's not going to work. So I immediately just drop this one. It's not going to work. The negative 3 might work. Let's try it out. We know it's not going to, but I'm just saying if I was approaching this as a student. So bring down the 7, right? Multiply by negative 3, negative 21. Subtract 21 from 18. It's a negative 3 times negative 3 is 9. Let's see, that's 21. And now you can see that's not going to work either. Right? Because negative 3 times 21 added to 9, negative 9, sorry, and it's not going to work out. So now I know that I'm busted on the 3's as well. So I go to the 1/7 and the 2/7. Now remember what I said in one of the earlier videos on synthetic division. If you start synthetic division with a fraction like 1/7, which we're about to do, you really want to be very aware that fractions really suck, right? You don't want to deal with fractions for a long period of time. And so if the fractions don't cancel out immediately, which they do in this case, 1/7 times 7 is 1, but then I get to 19 and I see, that's going to be a 19 over 7. It's not that you throw this out. I would just move away from it right now and then try the negative 1/7. If I have to, I'll go back to that one, but generally speaking, if you just walk away from it and try something else, it might work out. 18 minus 1 is a 17, but this will be a negative 17 over 7, and that's unfortunate. So again, I'll walk away from that one. I'm not going to cross out the plus or minus 1/7. Instead, I'll just move on to the 2/7. So let me try 2 over 7. Again, we're going into 7, 18, 12, and negative 9. And in both of those cases, you end up very quickly with fractions. And so I will move on. I haven't exhausted those possibilities, but I'm still going to try to keep the number small. So I'll go to 3/7. And then we know that that's actually going to be the winner, but let's just go ahead and do that. So I'm going to put a comma here and put plus or minus 3/7. And here we go. Now this starts to look good because I'm trying the 3/7, brought down the 7, multiplied by 3/7, it becomes 3. Add those up, it gets 21. 21 divided by 7 is 3 times 3 is 9. And you get back to a 21 again, which is awesome. And you multiply that by 3/7, again, you'll get to 9 and winner. So notice that avoiding the fractions really did help out. It's not that you won't have fractions, it's just that it really helps out to avoid them. And so now I know x minus 3/7 must be a factor as well. I'm going to go back up here. I'm going to erase all this other stuff. I know that x minus a 3 over 7 must be a factor. And I'm left with some polynomial. Let's see what the polynomial looks like. Oh, it's a 7, 21, 21. 7x squared plus 21x plus 21. And you say, wait a second. That's not what we had. You're right. It wasn't. But it is. Because if you factor a 7, notice those all have a 7 in common. If you factor a 7 out of each of these and park it, instead of parking it out front, if you just move it into this factor here to where it multiplies both objects by a 7, you'll get this. X plus 2. 7x minus 3, and then now you have an x squared plus 3x plus 3. Very nice factorization. And then you say, well, can that factor, because that's a quadratic, and you look at b squared minus 4ac rather than just trying to factor, you get 9 minus 4 times 1 times 3, which is negative, so no, that does not factor over the real number system. And this is where you stare at this and say, wait a second. I just learned a brand new theorem that said I could factor that into linear factors. Why are you telling me that this cannot be factored any further? And I'm not telling you that. What I'm saying is that what you are left with is what we call an irreducible quadratic. That x squared plus 3x plus 3 is considered to be an irreducible quadratic, but you can actually factor it over the complex number system. I'll show you how. It's better to see the factorization with an easier example. So you know how to factor this. You know this is going to be x plus 2 times x plus 3. We know that. But there's another way you could produce that factoring. If you let it equal to 0 and use the quadratic formula, you would get the following. Opposite of b plus or minus square root of b squared minus 4ac all over 2a. And that would be a negative 5 plus or minus the square root of 25 minus 24 is 1 all over 2. Or in other words, negative 5 plus or minus 1 over 2. So therefore x is either negative 5 plus 1, which is negative 4, divided by 2, or x is equal to negative 5 minus 1, which is a negative 6, divided by 2, which is negative 3. Moving everything to one side, you get x plus 2 is equal to 0, or x plus 3 is equal to 0. Those are your factors, x plus 2 and x plus 3. So really, that's how another way you could factor this is using the quadratic formula. I don't know if you've ever known that, but it is actually very true. The quadratic formula will actually give you your zeros. And in the process of giving you your zeros, it gives you your factors. X minus your zeros are your factors. So using that same idea, if I then changed it and I said, okay, you know what you actually have? You have x squared plus 3x plus 3, and you need to factor that, you would say, okay, let me set that equal to 0 and use the quadratic formula. I'll take the opposite of b plus or minus the square root of that b squared minus 4ac all over 2a. When you do this, you would be very aware that you have an imaginary number, right? 9 minus 12 is negative 3. So you have a square root of a negative 3 right here, all over 2. Remember, the square root of negative 1 is I, so you could rewrite that as the square root of negative 1 times the square root of 3, or in other words, I times square root of 3. And so I can say, oh, therefore, x is equal to either a negative 3 halves plus root, I'll say I root 3 over 2, or x is equal to a negative 3 halves minus the I root 3 over 2. Moving everything to the left-hand sides, just like we did over here, we will get our factors. So adding 3 halves to both sides and subtracting I root 3 over 2 from both sides, you'll get your first factor. Again, adding 3 halves, and now adding I root 3 over 2, you get your second factor. And here you have your full factorization of your polynomial. So let me go ahead and write that down up above. In fact, let me write it cleanly up above because we kind of butchered all this handwriting here. So all this I'm going to erase now. Get that out of the way, get that out of the way. And my final set of factors here are going to be, and that is our full factorization. X plus 2 times x minus 3/7 times x plus 3 halves plus I root 3 over 2 times x plus 3 halves minus I root 3 over 2. It's a lot of work, but it is a full factorization into linear components over the complex number system for the polynomial that you see on the left-hand side, which I will not read out. The way it's done, again, you use rational roots theorem to at least get that power on that polynomial down to a square. Once you get it down to a square, like a irreducible quadratic that we had right there in green, x squared plus 3x plus 3, for that irreducible quadratic, you go ahead and use quadratic formula to find what the actual factorization is. You just set it equals 0, find how the what the roots are via the quadratic formula, and then write your factors. Something very special about these factors that we're going to talk about in the next video is that these two numbers, let me highlight them, this number here and this number here, are very special. And we'll see that in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.